Okay, we're on day 2 of the last section of chapter 8. We're looking at comparing linear, exponential, and quadratic models. Okay, so today we're going to see some real world scenarios, and we're supposed to determine whether they are linear, exponential, or quadratic. And I can tell you right now, if it's the real world, it's not as precise as a perfect equation. This reminds me of our linear equations when we had a scatter plot, right? What did we put in a scatter plot? What did we call those lines we put in a scatter plot? 2 words.
Random points.
No, they were not random. We looked at a scatter plot, remember? Here it was like this. And what did we do with that?
Best fitting line.
There it is, say it, Jeremy.
Best fitting line.
Best fitting line. We said, oh, let's draw this perfect thing, and now we'll write an equation for that, remember? So that's kind of what's happening today. With an actual equation, you will see perfect addition, right? Or perfect multiplication. But in the real world, sometimes we have an exponential situation, but the numbers aren't totally perfect. And that's called experimental rather than theoretical, right? The real world is like an experiment where you gather data. So the experimental data, we might have to put a best fitting line in it. Could we also have a best fitting parabola? Yes. Could we have a best fitting exponential curve? Yes, so that's what we may have to do today. And you may have to do that here. So, any thoughts on this one? Chris?
Well, 120 through 260, and it's 140.
And what's this one then? 260 to 360.
100.
Okay. And what's 360 to 500?
140.
It is exactly, so this is looking so perfect. And what is 500 to 615? It's 115, so it's not quite the 100 we saw over there. Right? This is actually 115. And what is this? 145. So it's not quite the 140. So would it be okay with you if we just kind of called it 140? No? It's 145, isn't it? So in the real world, this is real world data. This is a flower store that is selling roses. And each year, every other year, they have something different happening. Do you see that? In one year, they sold 140. In the next year, they sold 100, and then they sold 140, and then they sold about 100 again, right? And then they sold about 140 again. So we could kind of say, I want to see what happens when we do this. What would you do next to try to determine this, Jeremy?
Well, actually, couldn't we take the mean of all of that to get the...
Well, what if we learn in our patterns? I mean, do we have a constant addition right here? But do we have a little pattern going on with this? We do. So let's look at the second difference. Why not, right? What's the difference between these two?
40.
And these two?
40. Negative 40.
It's negative 40. Is this difference really 40? Oh yeah, it is. I'm sorry. You got it. 40. Negative 40. What's this difference?
100.
Wouldn't that be negative
140 minus
positive 40?
This is pod? Well, it depends on how you're stating the difference, huh? So going from 140 to 100 is actually negative 40. From 100 to 140 is positive 40. From 140 to 100 is negative 40. And from 100 to 40 is positive 40. Does that look familiar to us? What kind of an equation do you think this is? Chris, what are you saying?
C.
You say linear. Why are you saying linear?
Because it shows a difference term, constant difference.
So you're thinking that the difference is kind of more found in the first difference? If it's linear, it would be the first difference, right? Lexi, do we have a constant second difference? Yeah, we don't really have a constant second difference. That's interesting. And Liam? Quadratic. So it looks, as we graph it, to be linear. So the average is probably somewhere around the 120s. average increase in number of long stem roses sold each year. Which graph here shows a quadratic model? 3, 2, 1. Good, you know that. Which graph here, or what is this graph called? 3, 2, and 1.
Exponential.
That's right, D. And name the type of model suggested by this. I just showed you a sample of this. 3, 2, and 1. A, absolute value. And finally, this one here, which one shows an exponential model? 3, 2, and 1. Good. Exponential in a negative kind of way, right? Okay, let's identify and write equations for these models. Just looking at this table of points, what is your first educated guess as to the type of equation, Dylan?
That I would say is
You're looking at it and you would immediately say maybe exponential. What would you say, Jeremy?
Quadratic.
Why are you saying quadratic?
Because it's increasing left and then going.
All of a sudden we go 1, 0, and then back up to 1. Does that feel like a vertex there? Like we've made a change, right? So how could we confirm it? That if we think it's quadratic, that it is? What would we do? Well, you could graph it, but how could we do it just mathematically instead?
find do the thing.
Okay, so do we have a pattern in the domain? The x values are going increasing by what? 1. By 1. So there's a beautiful pattern. So we can now look at the y values. And if we think it's quadratic, then we won't see a constant difference until the second difference, right? So what is 9 minus 4? And 4 minus 1? And 1 minus 0? And 0 minus 1? Okay, what is 5 minus 3? And 3 minus 1? Yay. And 1 minus a negative 1. So do we have a constant second difference? We do. We have a constant second difference.
Wait, 1 minus, oh, no.
Let's take a moment to try to write the equation. So you're going to be asked to do that today. And quadratic equations are the most complex ones you've learned. So they're going to keep it basic. Yay. Right? So we know that the model for the quadratic equation, you've already said y equals a x what? Squared, ax squared plus bx plus c. Okay, so what can we look for right away? X, we already have a bunch of x's. When you look at the model, is there any point that just jumps out at you in the model? Wesley? We know C. C is what? The y-intercept. Look at the table. When you have a y-intercept, you walk nowhere and you just fly somewhere. So the y-intercept for this is? 1. 1. Here it is. This equals C. So we can come down here and put 1 in right here, plus 1. This one is actually a little more complicated than the others that we'll do later. So because it actually has a y-intercept, most of them are simply just ax squared, and you just find the a, which is nice. Here's a little hint, you might have seen it already. A is half of the second difference. Okay, so jot that down. If a is half of the second difference, we can see the second difference here is 2. So what's half of 2? 1. So we already know that the number in front of x squared is 1. So we could just write it that way, x squared. Now if there's a b, we don't know it right here yet. And so we've narrowed it down to this equation so far, since we've just learned that a is the half of the second difference. So how could we find this b right now? Tatum? Good. Plug in a known point. Excellent. If we plug in one of these xy pairs up here, we will narrow this equation down to just a single variable, b. So which point would you like to plug in?
0.
Okay, she wants to plug in this point because that 0 is so nice. So 1 equals 0 squared plus, b times 0 plus 1. What happens to the b? it got wiped out by the 0. So that's a fun choice, but it's not very useful because our b got wiped out by 0, right? Wesley?
Use 1, 0.
Okay, he wants to use 1, 0. So this second choice here allows y to be 0, but b is 1. 1 squared plus, did I say b? I mean x is 1. 1 times b plus 1. This is interesting. 1 squared is?
1, 1.
So we end up with 1 plus another 1 over there, which is 2. So we have 2 plus b equals 0. So what is b? Negative 2. Ooh, interesting. So we can say negative 2 equals b, and now we bring it back up and say y equals x squared minus 2x plus 1. You will not have to do an equation like this on your own. You will simply have to do ones that have no b, okay? Chris? Okay, and take down this table and try to determine what type of equation this is. We really have two choices. You're either looking for a constant difference in the first or second difference, or multiplication, right? So what do you think, Casey? Exponential, why?
Because it's like the 1, it goes down to, and then half of 1.
Okay, so what are we multiplying by? Do you know?
1/2.
1/2. And you can determine it like this. You can say 4 times something times b equals 2, right? 4 times something gets you to 2, and so we can divide both sides by 4, and b equals 1/2. So if that's true, is 2 times a half equal to 1? And 1 times a half equal to 2.5? Right here, yes, times a half. And 0.5 times a half is 1/4. And I know this is a decimal situation, but we have this constant ratio. Okay? Again, you could look at it as 2 over 4 equals 1 over 2 equals 1/2 over 1. You see that constant ratio, and you know this is exponential. So can you write the equation? Who remembers again the model for exponential? Y equals b to the x. Good. And so remember in that period of time where you were writing these exponential functions, you remember the one that pops right out at you in the table? Which one, Jeremy?
Linear.
This is not linear, this is exponential.
But
And there's
no.
some-
Oh,
There's
okay.
something in this table that's jumping right out at you that belongs in this equation. Hannah? 0, 1, 0, 1. So when you plug in 0 for your exponent, what happens to the b value? It becomes a what? No! Any number to the 0 is? 1. Okay, so when we plug that in, we can say y equals a times b to the 0, right? Or y, oopsie, we know what y is. Y is 1, right? 1. 1 equals a times 1. So what does a equal? A equals 1. This is a. And you've done this before, back in 8.3 or something like that. So we say y equals 1 times b to the x. So we need to figure out b. Who knows it already? Because we've already found it, but you may not know it. You may not remember. Okay, you don't remember. Okay, so how can we find it if you don't remember at this point what it is? Look at our equation. How can we find it? Plug in a point again, right? But let's plug in kind of an interesting point. Which point should we plug in? Negative 1 and 2? Negative 1? Okay. Ooh. Okay, so if we plug in negative 1, 2, right here, we're saying that 2 equals, we don't even need the 1, do we? 2 equals some number to the negative 1. What does that number equal? This is interesting. So we would have to now say, what is a number to the negative 1? Right, I'm moving this over here so I can do this. There it is. This actually says 2 equals 1 over b, doesn't it?
So it's 40.
40. So what fraction, or what number I just gave it away, there's a fraction that we would place in for b that would cause the whole value here to equal 2. What would that be, Liam? 1/2. And where did we see 1/2 already? There it was. You should recall at this point that that constant factor is your b. So the equation is y equals 1/2 to the x. We just did it a really hard way. Once you know your constant factor, you know your b. This is it.
We didn't have to do it, we just got it.
2 from 4.
Okay, try it again.
As the x increase, the y's increase.
What's the difference between these two?
Maybe 12.
Do you see any constant change here?
Yeah, the y's are increasing.
Plus
2.
2, plus 2, plus 2, plus 2. This is constant. What type of equation is this? Linear. Who can write it? Chris? Yes.
Y equals
What is the 2? The 2 is the slope. It's rise over run, but this run is just 1. The 2 over 1 is 2. So 2x, and then you know the y-intercept?
Yeah,
Minus 1. Good, here's your y-intercept in the table. Okay, and the next one.
Because it's shaped, like, the 8, you go back here to,
And then all the way to 0 and back up. So you're right, it's a U shape, so it feels quadratic. So how would we know for sure? We're going to check for the second difference, okay? So what is 8 minus 2? 8 minus 2 is 6. You're dividing, but we're just subtracting right now. And then 2 minus 0 is 2 take away nothing? 2. And 1 take away 2? Negative 2, right? And 2 take away 8? Negative 6. And now in the second difference, what's 6 minus 2? 4. And 2 minus a negative 2? 4. 2 minus a negative 2. And then negative 2, subtract a negative 6, which is negative 2 plus 6, is 4. So there it is, second difference. Okay? The vertex is at 0, 0, which means the y-intercept is at 0, 0. So there is no visible b or visible c in the equation. We have y equals ax squared. And so how do we find the a once again?
second, it's half.
We said half of the second difference, so you should know that right now. We could say y equals 2x squared. And if you couldn't remember that, you could always plug a point in to find that. Okay, one real world problem. You're basically, again, using a big real world scenario today and identifying what kind of equation is this out of the 3 choices we've been working with, and then write the equation. Okay, so there's your final equation. And we know that each line costs $1.85, but there is a starting fee of $3 for an ad, is what this is saying. Okay, and there you go.